All right, let's talk a couple of brief formulas you can use to analyze the refraction of light. The first one is the definition of index of refraction. This letter N is what we use to signify that. But it's defined as just a ratio between the speed of light in a vacuum and the speed of light through this other substance that's slowing it down. Okay, so the speed of light in a vacuum is 3 times 10 to the 8th meters per second. That's a rounded version right there, okay? But for all practical purposes, that's good enough, okay? So that's how fast light is traveling in a vacuum, and it's essentially about how fast light is traveling through the air, okay? Because unless the air is drastically changed in terms of its density, it doesn't affect it that much. Okay? Now this down here is the speed of light in some sort of medium, whether it's glass, water, plastic, whatever, all right? And notice that if the speed of light in a vacuum is always going to be bigger than the speed of light through some other substance, it's always going to be faster on top than it is on the bottom, then this number is always going to have a bigger numerator, which means it's always 1 point something. Okay, so you'll never get an index of refraction that's smaller than 1. That would suggest that you have some substance where light can move faster than it can in a vacuum, and that is not something that matches our reality. Okay. So let's throw a couple of numbers in here. Let's say I'm dealing with flint glass like we did in the last video. Its index of refraction is 1.52. So this is a simple little formula with 3 variables, but we already know that this is a constant right here. This is one of those things that we know for a fact how fast light goes in a vacuum, and this is something you can look up. I mean, this is research that's been done on virtually every substance that light passes through, so all these values are out there, but it's pretty easy to take these two things and figure out how fast light is traveling in other substances. So if I was trying to figure this out for flint glass, I would look up its index of refraction, which is 1.52, and in your homework you're going to notice there's a small chart there that has a few of these common values. All I'm going to do is set up this ratio. 1.52 equals 3 times 10 to the 8th over V. I just have to solve it for V. And just make sure you don't mess up on the algebra here. We're going to set this equal to a fraction over 1. We cross multiply. So essentially 3 times 10 to the 8th times 1 equals 1.52 times V. So I'm going to have V end up being 3 times 10 to the 8th divided by 1.52. Okay, when I throw that into a calculator, it's going to give me a big number, and it's really big, but it just isn't quite as big as that one right there. I end up with 1.97 times 10 to the 8th. Those speeds are still on the same order of things, very, very fast. Okay, it's just this one's a little bit less and enough that we can actually measure it. Okay, there's the velocity of light, speed of light as it travels through flint glass. It slows down a little bit. Okay, so that's one of our simple formulas we can use to analyze refraction. The other one is something known as Snell's law. And Snell's law you can look up in your physics book. You can also look it up online. This deals with the angles that something comes in at. So I want to remind you, in the last video we talked about how a light ray coming in from air to glass, air has an index of refraction of 1. Okay, basically just like a vacuum. Glass has an index of refraction of 1.52. It substantially slows it down. Well, what's going to happen is this angle, okay, we'll call that theta 1, is going to get squished down. It's going to get pulled towards the normal like this, and we can actually figure out what that is. Snell's law takes these two things and these two things and relates them to each other. So the formula for Snell's law is N1 sine theta 1 equals N2 sine theta 2. And what you want to do is just make sure that the 1s and the 2s go to the right spot. So this is my incident angle and my incident substance. Okay? This is my refracted angle and the substance through which it refracts. Okay, so as long as we get those matched up, this is pretty easy to do because most of the time you can look these things up. Okay, we're just analyzing what would happen. So, for example, if we set this one up here, we would say N1, that's the index of refraction in air, which is a value of 1, doesn't change the math at all. Sine theta 1, well, theta 1 happens to be this one here. Let's say this was 40 degrees. Let's make up a number. So let's say it's coming in at a 40-degree angle. Okay, so I put sine of 40 right there. Once it hits that glass, it's going to go into a much more dense substance. Okay, here's the N value, so it's at 1.52 now, and it's going to refract to a much smaller angle. It's going to shorten up and get closer and closer to that normal plane. Okay, now all I have to do is algebraically solve this for theta 2. So just don't let the algebra mess with you. It looks a lot worse than it really is. I'm going to divide by 1.52, and most of you at this point would feel comfortable putting that right there into your calculator, and you just get this decimal, something you wouldn't recognize. Okay, so I'm going to get sine theta 2 equals whatever that decimal is. Now, I don't have a calculator handy real quick here, so I'm just going to write it came from sine of 40 over 1.52. Okay. Now, I want to get theta by itself. I need an actual angle, so I need that sine to go away, and the opposite operation here would be the inverse sine. So theta, or the arc sine, theta is going to be sine -1, and that's one of those functions you can see as a second function on your calculator, is sine -1 of whatever that value is. Okay, we plug all that in, and this is going to give me an angle of about 25 degrees if I round it. Okay, so what we're saying is it came in at 40 degrees, and then all of a sudden it's going to bend to 25 degrees. It really bends sharply towards the normal, and it's all based on how much that slows the light down. Okay, so in your homework you're going to be asked to use this one as well as the definition of index of refraction. Learn to mess around with that stuff and map it out, and hopefully you can look at these answers and be able to put some sense to it and go, okay, that makes sense. All right, I see when that's right, and I can see when something's way off and it doesn't match reality. Okay, so that's our basic structure for refraction of light.